All right, this is module 27, perpendicular bisectors. And basically what we're going to be doing is talking about some more properties with perpendicular bisectors and constructing something that's called a circumcenter and the properties of that circumcenter. So first thing I need to do is tell you a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. We're going to call that a perpendicular bisector. And we actually talked about this a little bit in a previous module, what a perpendicular bisector is. Bisector means it cuts it in half. Perpendicular means it creates four right angles. A point is equidistant, meaning the same distance from two figures, if the point is the same distance from each figure. So equa meaning equal, distance, distant meaning distance. Okay, so we have a couple theorems we're going to talk about. The perpendicular bisectors theorem. And in a plane, if a point is on the perpendicular bisector of a segment, then it's going to be equidistant from the endpoints of that segment. So if I were to say, first, I know point X is on the perpendicular bisector. The second thing I can conclude is that the point X is equidistant from A to B. So if we know that point X is on the perpendicular bisector, we can conclude that these two segments are going to be congruent. And again, perpendicular bisector means that it's perpendicular and that these two lengths here are going to be congruent. Now, the converse of this is also true. In a plane, if a point is equidistant from the endpoints of the segment, then it is on the perpendicular bisector of the segment. So the converse, you know first now that point X is equidistant from points A and B on the segment. The next thing you can conclude is that point X is on the perpendicular bisector. So for example, if we know that these two distances here are the same, we can conclude that point X lies on the perpendicular bisector. So again, perpendicular bisector. We are given that these 2 points are, or these two distances are congruent first, or the same, or equal first. That means that X is on the perpendicular bisector. And again, since these are perpendicular bisectors, we can say that these two segments here are congruent, and that goes for this one as well, for the regular and the converse. Okay, so I have a figure here, and what I'm asked to do is I'm asked to find the lengths of RS. So what do I see? I see that I have a perpendicular symbol here, and that ST's length is congruent to TU's length. So that means R lies on the perpendicular bisector. So if I know that point R is on the perpendicular bisector of SU, what can I conclude from that? Well, that SR and RU's length are going to be equal, so I set them equal to each other and solve for X. Once I solve for X, I can take this amount and plug it back in to find out what the length of RS is. So I do that, I substitute, and then I equal 39 units, a length of 39 units. So that's using the perpendicular bisectors theorem. Okay. What is the perpendicular bisector? Well, how do we know that it's the perpendicular bisector? Because we look for the segment that creates a perpendicular segment. So we know because of this right angle here, it's perpendicular. It bisects this entire segment length here. So we know it's perpendicular and it bisects. Therefore, RT is your perpendicular bisector. So RT segment. Okay. So in the diagram, I give you that BE is a perpendicular bisector of AC. That's what's given. BE is the perpendicular bisector of AC. So we know automatically that this is congruent to this. We also know because we're given DA is congruent to DC. And we also know that we have a perpendicular a perpendicular intersection of lines here with AC and BE. Okay, so which lengths in the diagram are going to be equal? Well, there's two obvious ones because of the perpendicular bisector. The one set is not so obvious because you have to use the actual theorem to prove it or to show it. So we can automatically conclude, because it's on the perpendicular bisector, that AE and EC are congruent. So that's pretty easy. We can also conclude that AD and DC are congruent as well. That's pretty easy because it's labeled in the diagram. But this guy here, he's not labeled in the diagram, so we would have to actually show that or conclude that. Well, since I know that BE is the perpendicular bisector of AC, because of the perpendicular bisectors theorem, we can state that this length here is congruent to this length here, because B is going to be equidistant from A and to C as well. So we know that they are congruent. So this one's the one that you have to dig a little bit in terms of finding the information. Okay, so the next thing, do we know that D is on BE? Well, here's the thing. We know that we have a right angle created here. So that means that this has to be perpendicular and create 4 right angles. If we know that these two lengths here are congruent, we can absolutely conclude it, because it's equidistant from A to C. D's point is equidistant from A to C. So here we're using the converse of the perpendicular bisectors theorem, because we know the lengths are equal first. That means we can conclude that D is going to be on the perpendicular bisector of AC. Okay, next it says tell whether the information in the diagram allows you to conclude that C is on the perpendicular bisector of AB. So for example 1, I automatically see that this guy here is labeled as congruent to this guy here. Problem is, I don't know what that angle is. I do know that these 3 lengths, 1, 2, 3, are all congruent. But that doesn't tell me anything about what this angle is here. And that's the most important thing. What does that angle have to be in order for it to be on the perpendicular bisector? Well, it has to be a right angle. It's not labeled as such, so we don't know if it's a right angle, so we can't conclude it. No perpendicular angles. What about example 2? All right, so we have all the labeled information. We know that these two segments are going to be congruent because of the labeling. We know that this is perpendicular here. We also know that these segment lengths are congruent as well. So we're asked, can you conclude that C is on the perpendicular bisector of AB? Well, since we know that this is perpendicular and these two are congruent, that means it bisects. That means absolutely you can conclude that that length is going to be congruent to that length. So yes, you can. Okay. This is going to be important when you do constructions, and we're going to be doing that later on, obviously, in a second video. But the thing you need to know is what concurrent lines are and a point of concurrency. So we say when 3 or more lines, rays, or segments intersect in the same point, we're going to call them concurrent lines, rays, or segments. The point of intersection of lines, rays, or segments is going to be called the point of concurrency. So if I draw 3 line segments and they intersect somewhere here, we call that the point of concurrency. And this is going to be evident when we do constructions and in the next slide as well. So we have concurrency of perpendicular bisectors of a triangle. We just talked about perpendicular bisectors. Here's your next theorem. The perpendicular bisectors of a triangle are going to be concurrent or intersect at a point that is going to be equidistant from the vertices of the triangle. So I have this figure here. And all the labeling of it, I have all my perpendicular bisectors that are constructed. I have a perpendicular bisector here, and a perpendicular bisector here. So if I know that those are perpendicular bisectors, and the reason I know that they bisect is because each one of the hash marks is labeled. So let's go through the figure and see, okay, we know AB and DP are going to be perpendicular just by the labeling of it. We know AD is congruent to DB by the labeling of it. BC is perpendicular to EP by the labeling of it. BE is congruent to EC, again, by labeling. AC is perpendicular to FP by labeling. and FC is congruent to AF by the labeling. Since we know that all of these are perpendicular bisectors, they intersect at a point of concurrency, which is P. Here's your point of concurrency. And if you apply the perpendicular bisectors theorem in this, all of these lengths, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, are going to be congruent. So that's what the concurrency of the perpendicular bisectors of a triangle state. That AP is going to be congruent to BP, which is going to be congruent to CP. You construct the perpendicular bisectors, they intersect. That point of concurrency is going to be equidistant from each one of the vertices. Okay, so moving on. The point of concurrency of the three perpendicular bisectors has a special name. We call it the circumcenter. And the circumcenter, P, is equidistant from the three vertices so that P is the center of what's called the circumscribed circle. And you'll be constructing that as well, and you'll see what it is a little bit later on. So we have circumcenter and circumscribed circle that pass through all three vertices. And you can think of the equidistance as kind of a radius of a circle. You'll see what I mean in a second. Okay, so here is my wonderful constructed perpendicular bisectors. Again, I have my point of concurrency at P. AP's length is going to be congruent to BP's length, which is going to be congruent to PC's length, or CP's length. Okay, so P is going to be equidistant from points A, B, and C. Okay, if you use this point of concurrency, the circumcenter, you can actually construct what's called a circumscribed circle. And the reason it's possible, think of this length here, again, as the radius of a circle. Well, if this length here is congruent to this length here, and this length here, and we continue that all the way around, all the way around, all the way around, you're going to be able to construct a circle that touches each one of the vertices of the triangle. And we call that the circumscribed circle. And we call it the circumcenter P. Okay, so the other properties that this has is evident here. Since we know that the circumcenter is equidistant from the vertices of the triangle, we can say if we know that BP is 7.5, that means BP is going to be congruent to AP, which is going to be congruent to CP. So all of the lengths are congruent. So what are we asked to find? We're asked to find CP's length, and we're asked to find BE's length based on the labeling. So we know this one's pretty easy because it's the circumcenter and it's equidistant from each one of the vertices. The next thing we know is we know EC is 12. Well, based off of the labeling, because it's the perpendicular bisector, if we know B or EC is 12, that means BE has to be the same thing because it's bisected. That's why you have the perpendicular bisectors. So this would be 12 as well. Okay, this is important again when we do constructions, which is going to be in the next video. There are three cases that can actually happen with circumcenters, and it happens with the three different types of triangles. In an acute triangle, your P, your circumcenter, is going to be inside the triangle. In a right triangle, when you construct your perpendicular bisectors and your circumcenter, that's going to be on the right triangle. It's going to be literally on your right triangle. And in an obtuse triangle, P is going to be outside of the triangle. And I think one of the ones that is the hardest to do in constructions is the obtuse triangle. And there will be an example of that in the video. So, now we're going to do constructions. So what I want you to do is to go to the next video, and I'm going to demonstrate what perpendicular bisectors is, constructing a perpendicular bisector, also constructing a circumcenter, a circumscribed circle, and I will do it for a few of the triangles that are given.